So let's take a look at another example of functions and try to make sense of what an inverse function would really mean. So if my domain is the set of all of my x's and my range is the set of all of my y's, the connection is my function that's defined by the equation g of x is equal to 1 divided by x. So I can rewrite this as y equals my function equation, 1 over x. So this is our function. You give me an x, the function itself will give you a y. But we want to find the connection that's going the other way around. We want to go from y to get an x. And in order to do this, we need to solve our equation for the value of x. We need to get our equation in terms of y. So, using the order of operations in the reverse order, we can first create our zero pairs, which we don't have any. And then we take a look for our 1 pairs by multiplying by the reciprocal. So I'm going to multiply by x over 1. Simplify on both sides, and it's going to give me x times y is equal to 1. And again, I want to solve for x. I want to get x all by itself. So I'm going to divide by y on both sides, and my x equation is equal to 1 divided by y. What we produced is a function of y that gives us an x value. The range now becomes the domain for the inverse of g of y is equal to 1 over y. So, again, this is the same equation, I'm just rewriting it, I'm renaming it. Instead of saying it's going to be the inverse of g of y, now I'm saying the inverse of g of x is 1 over x. The function takes us from the domain to the range, the original g of x, from the domain to the range. The inverse takes us from the range, from that point in the range, to the original value that was in the domain. The original range becomes our new domain. And we can see that these values are inverses of each other, but they're also identical to each other. So taking away that work, I see that I have a domain and I have a range. Let's test some points. Let's see if these really truly are inverses of each other. So if I input 1 into my original blue function, g of 1 is equal to 1 over 1, which simplifies to 1. So my g function maps from 1 to 1. Let's test it in my inverse. The inverse function of 1 is 1 over 1 with substitution, simplifies to 1. So it's correct. The inverse function maps from 1 to 1. It works. They're inverses of each other. But let's test another point. G of 5, let's say. 1 over 5 is equal to 1/5 simplified. G maps from 5 to 1/5. Testing this theory and testing our inverse function, what should happen is that the 1/5 maps to the 5. And let's test. I input my 1/5. 1 divided into fifths means I would have 5 1/5 sections. So it's correct. The inverse function of g maps from 1/5 to 5. So let's take a step back and see how these functions behave on the coordinate plane. So I can see that my blue function is mapped, but it's also the same equation, same function as my red function, or as my inverse g function. The red line that is on the grid that goes through is our identity function, y equals x. And what you can see is that on either side of the y-axis, both on the positive side and the negative side, my red inverse function and my blue function are reflected about the identity function line. They're inverses of each other. However way I look at it, if I fold them both up across each other, so the identity function is my line of symmetry, the points match up to each other. And I can test this with a point 1. My domain 1 goes to my range 1. But then inverted, taking another look at it, if I were to look from my range going to my domain, it's the same point, it's the same value. So these two functions are inverses of each other on both the positive and the negative side. So, compositionally, I can see, operationally, I can see that the composition of these functions should be my identity. So let's test it. I'm going to take my inverse function and input it within my original G function. I'm going to take the inverse, apply it in my regular function, and see that if I take 1 and divide it into 1 over x sections, I'm going to be left with x number of sections. So my inverse function composed within my original function will leave me with the identity function. It's true on one side, let's test it on the other. I'm going to take my original function, compose it within my inverse. So I have an inverse and my original working together. It's set up identically to the previous example. Taking 1 and dividing it into 1 over x sections is going to leave me with x number of sections. So my inverse function composed of my function leaves me with, again, x, my identity function. So whether you're using operations and breaking it down to the inverse, or you can use the graphical representation of identifying your domain and your range and seeing the mapping connection of switching the x and the y, you can see that using an inverse with an original function will compose together will give you the identity function. And that holds true with multiplication and addition operations, which are baby functions. I need and I use my inverse to obtain the identity.